All right, welcome. We're going to be talking about our final set of basic inference rules in sentential logic. 2 rules for disjunction, 2 rules for conjunction, and 2 rules for biconditional. You can think of these as introduction rules and elimination rules. For each of our new connectives, there is a way to introduce the connective and a way to eliminate the connective. Sometimes they're called introduction and elimination rules, although those aren't the official names we'll be using. So let's start with conjunction, which probably these two are the easiest. The first rule is simplification, which we're just going to abbreviate with S. And simplification tells us that if we have box conjunction circle, where box and circle are metavariables standing in for any sentence letter, any P, Q, R, S, and so on, or indeed for any well-formed sentence in the language. If you have box and circle, you can infer validly, therefore box. Or, and this is the same rule, if you have box and circle, you can infer validly, therefore circle, citing the same rule, S. So if we have a conjunction on a line, P and Q, we can validly infer that P. Or we can cite the very same rule, simplification, or S, and conclude that Q from P and Q. So this is obviously a valid inference. In English, the English equivalents are just intuitively valid. I'm not going to spend much time on justifying it. If we have a sentence that's true, Copper sniffs and Ollie digs, what can we validly conclude from that as a matter of logic? Well, we know that both of those things are true, Copper sniffs and Ollie digs, so we could conclude, well, Copper sniffs. We could also conclude Ollie digs, right? The introduction rule, as it's sometimes called, for conjunction is what's known as adjunction, or abbreviated ADJ. And adjunction tells us that if we have box on a line and then circle on another line, we can validly infer box conjunction circle, or box and circle. So if you have P on a line and you have Q on a line, you can cite ADJ and conclude that P and Q. You're just taking the contents of the two lines and conjoining them. If it's on a line, you know it's true or has been derived from something that's true. And so, given the truth table for conjunction, you can conclude that any two things you have on separate lines, the conjunction of those things is a true sentence in the language, which is why we can validly make that inference. So if you have in English, Copper sniffs, period, that's one sentence. Ollie digs, period, another sentence. Then you know both Copper sniffs and Ollie digs. Pretty straightforward. So those are your two conjunction rules. The left-hand rule, simplification, or S, is an elimination rule for conjunction, and the right-hand rule, adjunction, or ADJ, is an introduction rule, a way to get from non-conjunctive sentences to a conjunctive sentence, or a conjunction. 2 rules for disjunction. These ones are probably especially this first one, the one that requires the most explanation and motivation. But once you understand the truth table for disjunction, as we'll see, this rule becomes clear why this is a valid inference, even though it feels like magic. So this is the addition rule, or ADD, add. Sometimes it can be tempting to think, well, the add rule has to do with conjunction. Add rule is a disjunction rule. And the addition rule says that if you have some sentence, any sentence, simple or complex, anything that's well formed, alone on a line, box, you can conclude box or circle. Box, disjunction, circle. Where circle can be any well-formed sentence in the language. Circle could be the very same thing as box. It could be a different sentence letter if it's something simple. It could be something terribly complex. In other words, what addition tells us is if you have, in a particular case, if you have P on a line, you can cite addition or ADD and conclude P or Q. Indeed, you can conclude P or R, citing that very same rule. Or you could conclude P or S. Or you could conclude merely from P citing the ADD rule, you can conclude P or, if it's not the case that S, then it's both the case that T and not P, where that right-hand complex sentence there, which is a conditional, is itself the right-hand disjunct of that disjunction that has P as the left-hand disjunct. Why is this valid? Let me just run through an English example to give you, if you're not confused about why it's valid, when we do it in English, it'll be like, what? So suppose you have a sentence, JB went to the store, or me. Professor Barker went to the store. Suppose you know that's true. The addition rule says you can conclude either Professor Barker went to the store or Professor Barker took Copper to the vet. Now, how can that be? I didn't tell you anything about Copper in the first sentence or anything about whether he went to the vet. How can you tack that additional disjunct on? And indeed, ADD licenses inferences like this one. Professor Barker went to the store, therefore either Professor Barker went to the store or Copper went to the store. It also licenses this inference. Professor Barker went to the store, therefore either Professor Barker went to the store or Copper went to the moon. In fact, we could put, instead of Copper went to the moon, Copper is a square circle, if we wanted to, as our additional sentence, something that's obviously nonsense and false. So how can that be? Well, let's take a look at the truth table for disjunction, and it'll become clear why this is a valid inference. And this is going to be a particularly useful rule in our new derivations. So it's really good to, if you're stuck in one of our new sets of derivations, sometimes the reason you're stuck is that you have to introduce new content into the derivation that isn't in the premises and hasn't been given to you as an assumption, and the only way to do that is to use the addition rule. So if you look at our truth table for disjunction, remember that it's really easy for a disjunction to be true, and it's harder for a disjunction to be false. So long as at least one or the other, or perhaps both, of the two disjuncts of a disjunction are true, then the whole disjunction is true. That's what this truth table tells us. So in the first row there, under the circumstance that box is true and that circle is true, either box or circle is true. Okay, fair enough. That's pretty intuitive. But we also know, if you look at the next line down, if box is true and circle is false, then either box or circle is still true. Likewise, if box is false and circle is true, then either box or circle is still true. The only case in which the disjunction is false is when both disjuncts are false. And what this means is that you don't have to know the truth value of the second disjunct of a disjunction in order to immediately infer that the whole disjunction is true, if you know for sure that the left-hand disjunct is true. If you know for sure that the left-hand disjunct is true, it doesn't matter what the truth value is of the right-hand disjunct. And that's why the ADD rule says you can introduce any old disjunct you please onto something that you already know is true, and you can be assured that the result will be a truth. And remember that valid inferences are ones that are truth preserving. Necessarily, if the premise is true, then the conclusion is as well. It's this movement of truth in the premises to truth in the conclusion. And you get that given the truth table for disjunction by introducing any old disjunct onto a truth. You get truth preservation. So suppose you know, here's another way to put the same thing, that some sentence P is true. You don't know what P says, you just know it's true. Now consider the disjunction either P or Q. Yeah, that just came out of nowhere, P or Q, but just consider it, right? You do know that P is one of the disjuncts of the sentence P or Q, and we're also assuming that P is true. And given the truth table for disjunction, you know that a disjunction is true so long as at least one of its two disjuncts is true. Since you know that one of the disjuncts of P or Q is true because you're assuming that P is true, you can conclude that P or Q as a whole is true. Q may be false, or it may be true, or you may not ever know. Doesn't matter. It's a valid inference. So that's the add rule. You can think of that as our introduction rule for disjunction. Well, what about an elimination rule for disjunction? This one is fun and a lot more intuitive. Modus tollendo ponens, or MTP is what I'll call it. The MTP rule says that if you have a disjunction, either box or circle on a line, and then you have the negation of box or not box on another line, then you can conclude therefore circle. You can't conclude therefore not circle, that would be invalid. You can conclude therefore circle. In other words, this inference is telling us that if you've been told on a line, you have a sentence that says, here are your two options, P or Q. And then you have another line in which you know, well, P is not the case. Because you know that either P or Q must be true, and you know that P isn't true, well, Q must be true. That's the structure of MTP. It's a kind of process of elimination argument. Likewise, MTP can be run, this is the same rule, just applied to the cases when you have the negation of the right-hand disjunct. So if you have box or circle, and you have not box alone on a line, then you can conclude, then you have not circle alone on a line, then you can conclude that circle. Or if you have P or Q, if you've been given not Q, you can conclude that P. The negation of either disjunct alone on a line allows you to license. License is the conclusion that the other disjunct is true. You can break it off, so to speak. So in English, suppose you know that either Mr. Smith fled the country or else the butler murdered him. Mr. Smith is nowhere around to be found. You're like, using my detective skills, I know that either he fled the country, because he would be here if he were in the country, or I've always been kind of suspicious of that butler, or maybe the butler murdered him. And then you discover, well, Mr. Smith didn't flee the country. You know, ask around about his vacation home, and you're like, is Mr. Smith at his vacation home in Canada? And they're like, no. Like, well, then he didn't flee the country, I guess, because that's where he would be. So you can conclude he must have been murdered, if indeed you know those first two things are true. Or if you know that those are the only two options, Mr. Smith fleeing the country or he was murdered by the butler, and then you learn the butler definitely didn't murder him because he's got an alibi, say, then you can conclude, well, I guess he must have fled the country. So those are your two rules, ADD and MTP. The first is an introduction rule for disjunction. The second is two versions of an elimination rule. Whenever there's two versions, you cite the exact same rule. You don't have to cite anything else. You just cite MTP together with the line numbers at which the relevant sentences occur. Here are our final two rules. They're both inference rules for biconditional, and they're very straightforward. The first one is an elimination rule for biconditional to conditional, or abbreviated BC. which tells us that if we have a biconditional alone on a line, if we have a sentence of the form box biconditional or double-sided arrow circle, box if and only if circle, then we can immediately infer from that if box, then circle. Or if we know that P if and only if Q, then we know that if P, then Q. And this, of course, makes sense given what we know about the meaning of the biconditional and its truth table. We talked last time about the way in which a biconditional sentence is logically equivalent to the conjunction of two conditionals, one of which has the left-hand part of the biconditional as its antecedent and the right-hand part as its consequent, and the other conditional has the left-hand part of the biconditional as its consequent and the right-hand part as its antecedent. And so, of course, if you know P if and only if Q, you can conclude that if P, then Q, because P if and only if Q is kind of hiding within it already those two conditionals. And so, likewise, you could cite the very same rule, BC, to conclude if Q, then P. Either one. You know that both of those conditionals are, so to speak, hidden within the biconditional, so all you're doing is just pulling one of the two out. And you have a choice here about which one to pull out. Note that you have to apply BC twice in order to pull both conditionals out. You can't do them both at once. So just sort of keep that in mind. The other rule and our final rule is an introduction rule for biconditional, and this tells us that if you have if box then circle alone on a line, and then on a separate line if you also have if circle then box, then you can infer box if and only if circle, or box biconditional circle. Or with P's and Q's, if you know that if P then Q and you also know that if Q then P, then you know P if and only if Q. And again, this makes sense given the meaning of a biconditional. We could do the truth tables to prove it. I'm not going to do that in this video. I trust you get it. So those are our two rules for biconditional, BC and CB. Don't confuse them, they're different. Yeah, those are our new rules. So learn them. You should know them in the abstract and think about how they might be applied in derivations, because when we get back next week from the break, we will be making use of these rules in derivations. All right, enjoy the rest of your break, and I will see you guys on Wednesday following the break.